So if we put this into the formula, f of x plus h minus f of x all over h, here we would have 3 times the square root of x plus h minus 3 times the square root of x all over h. And we have an issue in this one that hasn't come up on any of the other ones. We can't expand or simplify the top whatsoever. There's nothing we can do to simplify it. And so we have no way to cancel that h out on the bottom. So we go back to a technique that you first learned in grade 11. Do you remember in grade 11 when you had to rationalize the denominator for when you had square roots on the bottom? And you have to like multiply. If you had a square root of 5 on the bottom of your fraction, you have to multiply by root 5 and root 5. But if you had 2 plus root 5 in your denominator, what did you have to multiply to get rid of it? And do you remember the special word for that thing? So this is, here we'll just go back in time. You have this question in grade 11. You were asked to rationalize the denominator. What did we multiply by? It's not just root 5, because if I multiply by root 5 and I distribute, I still have a root on the bottom. 2 minus root 5. And the reason we did this is because on the bottom, when we multiply this out, if we do it completely and FOIL it all out, we'll have, you can see that the middle terms would cancel out. You'd have a minus 2 root 5 and a plus 2 root 5. And those would cancel out, and the rest are already whole numbers, so the bottom would just become negative 1. Okay? Now, part of the reason you did that in grade 11 was to help prepare you for this right now today in calculus. Another part of the reason was historical, in that we rationalized the denominator because it was much easier mathematically to figure that out by hand than it would be to figure out the blue 1 over 2 plus root 5 by hand. Do we do either of those by hand anymore without a calculator? No. So the original purpose for doing that sort of got lost because we have calculators. We don't even learn how to figure out square roots by hand anymore. We could. I could show you, but we don't have to. But this idea, this and this, are called conjugates. And conjugates are the same binomial where one is positive in the middle, the other one is negative in the middle. And the reason for it is if you have anything where you're multiplying conjugates, well, this is just, the result is just a difference of squares. And if you square both things, what's going to happen? Your square roots will go away completely. So now going back to our question, we're not going to rationalize a denominator, but we are going to rationalize our numerator. So I would have to multiply by the same thing with a different sign in the middle. And I'd multiply the top by that and the bottom by that. Now, initially, this seems like it's just making things bigger and more complicated. And initially, that's what it looks like. We're going to multiply out the tops. It forms a difference of squares. On the bottom, I'm not going to multiply it out because I have an h already factored out of the bottom then. And my goal is to cancel out that h so I can evaluate my limit. Well, if we look at what happens on the top, we get 9x plus h minus 9x. And now we have something in the numerator. We can distribute that 9. Can you see that your 9x's are going to cancel out? And all you're going to be left with on the top is 9h. And since that h is factored out in your denominator already, you can simplify. And that's the key thing to using the definition of the derivative. that you can simplify that. And now, if you plug in 0 for h, will you be dividing by 0? No. And so we can evaluate the limit by plugging in 0, simplifying, and we get 3 over 2 root x. Right? You know how in the last ones I said we're going to learn a shortcut that these will take 5 seconds? This one's about a 9-second one. So it's a little bit more complicated. Find the slope or gradient of the tangent line to this function at y equals 4. Well, when we find our derivative gives us an equation for all the slopes of every single tangent line at every single point. So if we want to find it specifically at x equals 4, we'll find the derivative at x equals 4. We plug in 4 for x, simplify, and the slope would be 3/4 at that point. So in this unit, we're going to learn which functions can we find the derivative of easily, and how we can do those without a calculator and figure out the slope of the tangent at any point. But we're also going to look at some functions that we can't do without our calculator easily. And so what does it look like, and what does our calculator have that can help us? So one of the functions on your calculator is this one called n-deriv. So you can find it by going math 8. It calculates the slope of a tangent at a point. So we're going to look at this example. F of x equals sine 3x squared. First of all, can you even graph that? Do you have an idea what sine of 3x squared looks like? Let's have a peek, just because it's not just a regular sine graph, is it? So I'm going to clear out. We have sine of 3x squared. Zoom to trig. Have a look at this graph. Huh. It's exactly what I thought it would look like. Have you ever graphed something that's taking a long time and you're like, oh, I want it just to stop? You can push the on button and it stops whatever's graphing. Okay? I once misread a question and put something into my graphing calculator to see how long it would take, and then it started graphing, and then I realized I misread it, but I was curious how long it would take to graph, because if you didn't know about the on button, you have to wait until it's done graphing. It was about, I quit at 45 minutes. It was about 2/3 done. So what we can do, we hit our math button, go down to number 8, n-deriv, and it looks either like this, or you can type things in directly. So you need to pick a variable. We pick the variable x. Okay, we write our equation in here. Sine, oh, I have something I have to change on my calculator. My calculator is currently in degrees. All of the calculus that we're going to be doing is going to be in radians. There we go. So sine 3x squared, and we want to figure out at x equals 1. So it finds the derivative when x is equal to 1. This is nice proper notation as well. Negative 5.93, or negative 5.94 to 3 sig figs. I'm going to go back to the graph since I wasn't in radians and see if it, no. Oh, it is a little bit different. Yeah. Let's look at what this one would be in our calculator. Natural log sine of x squared plus x. That seems like something you can visualize the graph easily, right? Natural log sine of x squared plus x. Wow. All right, let's see if we can figure out what the derivative to this one is at pi over 4. So we go. Math number 8. Natural log sine. This one may or may not. X squared plus x. When x equals what value? Pi over 4. Enter. This came up automatically when I picked the n derivative function. And push enter. 0.437. So this is where you can practice some more. Whenever it says definition of the derivative, that's the Newton's quotient, is another name for the definition of the derivative. You're not supposed to use any shortcuts.